we're going to be focusing on three failures of classical mechanics. That is, all the mechanics learned about by about 1900. Everything after that point is called modern physics. So classical mechanics is about the motion of objects, and also we're going to discuss a little bit about the failures of heat thermodynamics and waves as well within that. So the first failure is understanding blackbody radiation. That is the energy given off by a heated object is the basic idea here. But in order to actually study it and come up with formulas, we have an idealized blackbody. So an idealized blackbody is an object that only absorbs radiation. So the way that they modeled this is you think of a cavity that's being heated up to some temperature, and it has a small pinhole, okay? And light can enter through this pinhole, and it hits one of the sides of this cavity, this empty area with some sort of solid barrier here. It hits the cavity wall and it bounces off, and it goes to another cavity wall. And the idea is it's going to bounce off many times before it can make it back to the pinhole. So that by the time it does exit the pinhole, it's reached an equilibrium with all the other light waves that exist in this cavity. Essentially, one light wave is the same as any other light wave within this cavity. Okay, so that's an idealized blackbody. Now, there's we're going to start off with how classical mechanics would have thought of this idea. So if you think of how many light waves you can fit into one of these areas, okay, and you remember that light that is more energetic has a smaller wavelength. So energy and wavelength have an inverse relationship to one another with light. So one way of putting this would be E is equal to h nu, where nu is the frequency, so E is equal to hc over lambda. We'll get to what these mean later, but h and c are constants, nu is the frequency, lambda is the wavelength. So smaller wavelength, bigger energy. Okay, but we'll get to that in a moment. But since this is smaller light waves are more energetic, you would expect you can fit more and more of these high energy light waves inside this cavity, then you can fit much less energetic light waves. So this gives rise to a very weird graph. It's generally known as the Rayleigh-Jeans law, and it creates what's generally referred to as the ultraviolet catastrophe. So on the y-axis you have some measure of intensity. It gets somewhat complicated, so we'll just call it an intensity and not worry what the units are. And then on this side you would have frequency, or you could use wavelengths conceivably. So we're going to call it wavelength in nanometers. And so at some point, at about once you hit around 400 nanometers, okay, so once you hit about 400 nanometers here, you enter into the ultraviolet region. Okay, so this is where the UV is, anything down to the right here, and this would be your visible region. Okay, So it's pretty normal, especially as long as you stay in the reds and oranges. So it's pretty reasonable, but then it goes crazy and it keeps going up and up and up in the ultraviolet region. So this would seem to say that for an object at any temperature, this graph does vary with temperature, but it will just shift this graph somewhat. But for an object at any particular temperature, you're going to have something like this graph, and the intensity continues going up past the UV region. So if this was truly the case, then objects just around us in everyday life would be emitting lots and lots and lots of ultraviolet and X-rays and so forth, gamma rays, radiation. Obviously, that's not the case. That we wouldn't be alive if it was, and so this is not an accurate representation in any sense of what we observe. Now, Planck, that is Max Planck, made an assumption in order for this to work out. And the assumption was that you have little springs almost vibrating, little springs on the side here, and they can exchange energy by emitting and absorbing light. So maybe this spring emits energy, and then this one over on the opposite side will absorb it. Okay, but there's a restriction here on how these oscillators or springs can absorb and emit energy. They always have to emit energy proportional to the frequency of light. So E is equal h nu. That equation that I mentioned earlier. So since E is equal to h nu, that's going to restrict what energy levels are available. So this is an example of quantization of energy because h is a constant. So energy is only available in these units of h nu. So that restriction helps to change this graph dramatically. So instead of getting a graph like this, instead you get a graph for something that's very high temperature. It would look something like this. So basically you have a portion here where it would be infrared and microwaves and so forth, and then it would peak at some point, and then it would continue to go down as you go to higher and higher frequencies. So you have going up and then going back down. So this means that there's no ultraviolet catastrophe. You don't have substantial amounts of ultraviolet radiation or gamma rays or X-rays being emitted by everyday objects. In fact, for an everyday object, most of the light that's being emitted by these objects are going to be infrared, so way off on this side, not even on the graph. So that helps explain how in day-to-day life this makes sense, and we can understand how this works. Welcome to the second portion of my video about failures of classical mechanics. So this is about the photoelectric effect. So the photoelectric effect is what occurs when you have two plates that are made out of metal, and light hits one plate, and then electricity flows, so I'm going to write that as electrons flowing down. And the way that this has to happen if electrons are flowing down this way is electrons must be jumping from this electrical metal plate to that metal plate. Okay, so you've got electrons jumping due to this light hitting the metal surface and causing electric current. So first, again, we're going to talk about the classical way that this would be understood and how that would result, and the quantum mechanical result, which actually explains the experiment. Okay, so the idea from classical mechanics is that, again, since you have this metal plate and you have light hitting it, that if the light is more intense, then it's going to cause more electrons to jump with greater velocity or speed. And the reason that they would give for this is that that when the light hits the metal surface, if it is intense enough, regardless of what its frequency is, if it's intense enough, it will jostle the electrons and make them shift around in sympathy with the light wave. And when this happens, it will cause the electrons to jump out of this plate and into this second plate. And the greater the intensity, the more often this will happen. And again, there's no dependence on frequency. The problem with this is that didn't happen. So there's two fundamental errors that this makes if you look at the graph that experiment would give you. So experiment would show something like this. You have the kinetic energy of these electrons, so their kinetic energy versus the energy of the incoming light. So we'll call that nu, or the frequency, sometimes called F, but we'll call it nu. So what it will look like is this. It's a straight line, okay, that intersects and ends at the x-axis. So there's some minimum energy that's required, or some minimum frequency, oftentimes referred to as the work function. So every metal has a particular frequency, and any light hitting that metal below that frequency will not eject electrons. Any light, regardless of its intensity, will eject electrons if it's above this frequency. So there were two errors in this classical mechanics thinking. The first is that from this graph you can see that not all light will cause electrons to jump from one metal plate to the other. The second is that there is no dependence on the intensity when it comes to the kinetic energy of these electrons. So how did Planck and Einstein in particular resolve this? Well, they assumed that energy is quantized. So they assumed that this energy is equal to h nu, where h is Planck's constant, is that same constant that fits the Blackbody radiation curve. And at the time, Planck thought it was just a curiosity, doesn't really mean anything physical as far as he was concerned, but Einstein was thinking, no, this actually does have some real meaning. So H times nu is the energy, and if you think of the kinetic energy as whatever is left over when the light, so basically the light's energy goes into one of two places. It either goes towards making the kinetic energy larger, or it goes towards ejecting the electron in the first place. So the idea is that you need some minimum energy to eject the electron, and then any excess energy above that goes towards the kinetic energy. And that was the central result of Einstein's paper. The last portion of this video about the failures of classical mechanics. So we're going to be talking about Bohr's theory of the hydrogen atom, noting that we have made great improvements since then on understanding both the hydrogen atom and atoms in general. But for simplicity's sake, we will keep with just Bohr's theory. So first, how did he come about to this theory? How did the question arise? So what happened was the astronomers and others were examining the spectral lines being given off by the sun. They noticed there are certain absorption lines that occur periodically in the sun. And also, if you look at diffuse gases in a tube that emits radiation, such as neon signs, for example, that you might see at stores and so forth, then they follow a certain pattern. And the hydrogen atom is the simplest among these. So that's what they started with. So if you want to understand that, Balmer is the place to start. He was a mathematician in the 1800s, primarily taught school to girls, and also taught at the University of Basel. But he was primarily a mathematician, but he did come up with this empirical formula which describes the emission lines for hydrogen. So it's 1 over lambda, that's the wavelength, is equal to some constant, we'll just call it R for now, times 1 over 2 squared minus 1 over n squared. And this idea was a little bit odd, but it accurately reproduced all the lines to very good accuracy. And this n also has a special relationship. So the relationship is that n is equal to any number greater than 3. That's a counting number. So 3, 4, 5, 6, and so forth. So if you actually were to plot this on a graph, you would see something like this might be your first line, and your second, third, fourth, fifth, sixth, until they just sort of all come together into one region here. They just sort of all bunch together. But this wasn't the only thing that was happening. There's also something else curious. There was another guy by the name of Lyman, and he figured out, oh, there's a very similar relation, except instead of 2, we have a 1. So 1 squared. And it happens, instead of Balmer's was in the visible region, Lyman's was in the ultraviolet region. And n behaves a little differently as well, so it's any counting number greater than 1. So 2, 3, 4, 5, so forth. But the spectral line is very very similar to Balmer's, except it's in the UV region. And there was yet a third series. And this series is called the Paschen series, and it has a 3. and it's in the infrared region. And the N can take in values from 4, 5, 6. So if you haven't picked up on a theme yet, the theme here is that this number can only take on integer values, in this case 1, 2, or 3, and this value also has to follow certain rules, and it can only take on integer values. So you've got what's called a quantization of eventually energy levels once we piece all this together. So Bohr was trying to understand how this would work, along with using Rutherford's theory of the atom. So Rutherford, using his gold-foil experiment, determined that most of the mass of a nucleus is in the center, and he posited that the electrons are flowing around that central nucleus, but they're not really in the center. They're just sort of in a cloud around it somehow. Bohr went a step further and posited that they are in circles. So it's like a little solar system, kind of. And you have these electrons flowing around the circle. Now, if you think of how this might work, then there's a problem, right? Because if you go back to your uniform circular motion section of last semester, you would find that force is equal to ma as usual. The acceleration associated with centripetal force is going to be v squared divided by r. That is a problem because we cannot have this acceleration here. And the reason why is that this is a charge, and so since you would have a charge accelerating because you do have this centripetal force, so you have an acceleration. So if it's accelerating around the center, then the theory and what we learned about electricity and magnetism would tell us that light would be emitted. And if light is emitted, then energy must be given off in order to conserve energy, because as by this point we know, E is equal to h nu. So what would happen is, as it's giving away this light energy due to this acceleration, it would spiral down to the center. And literally, you would just have the positive and negative parts, the nucleus, which has the protons and the electrons combining, and they would just form one thing in the center, and the atom wouldn't last very long. And of course, basically the universe would vanish in a flash of light. So that's not what happened, so we need to make sense of it. But this was just basically applying Coulomb's law and what we know about uniform circular motion. So, how did Bohr avoid this issue? Well, he made some assumptions. So, the first assumption is that electrons can only have certain orbits. They're quantized orbits. So orbits are only certain orbits are allowed, only certain energies are allowed. And furthermore, how do you select these orbits? Well, what you do is, if you were to try to fit a wave around this atom, only certain frequencies would fit. So if you were to do this, okay, so in this case, notice that when I hit the same spot again, it doesn't make a continuous thing. It's discontinuous here. And that's an indicator that if I continue going around and around, I'm eventually going to have the destructive interference is going to overcome this wave, and it's going to disappear through destructive interference. So only light waves that are continuous all the way around the circle are allowed. And so this restriction prevents many possibilities from occurring. The other thing is that if you think of what is the force, okay, so the force is equal to K times Q1 times Q2 divided by R squared, that's Coulomb's law, and the centripetal force is F is equal to mass times V squared over R. If you just substitute in the relationship for centripetal acceleration, V squared over R, and replace that for A. And if you set these equal to one another, then you can find a relationship, if you work at it, that will tell you what radii work to make these equal. For particular masses, of course, in this case the mass of an electron and velocities and so forth. But the central thing here is that only certain waves are allowed to go around the hydrogen atom. So if you work at this, you would be able to get a series of circles that obey this relationship, and each circle would have a particular set of frequencies that fit at on that particular circle, or what we would later call orbital or energy level. So, although we're not quite that developed yet because we're just at Bohr's theory of the hydrogen atom, but that is how Bohr explained that the world doesn't vanish in a flash of light, and he explained Balmer's theory, or Balmer's empirical formula, and showed that it makes sense. So the way that it makes sense is you get these energy levels out, and they would look like this. So what you have when the electron or the light's emitted is you have some electron here, and you have another electron above it, and these electrons fall down and emit light with some frequency. So this quantization results in only in your counting numbers appearing in all Balmer's and Paschen's and Lyman's laws, and it also gives rise to quantization. Right? So now we've discussed the three major reasons that quantum mechanics rose in the early 1900s and displaced some of the ideas from classical mechanics. There will be video links below and links to papers as well about these topics.